thank you for sitting back down again. It's always the biggest problem. We all like to talk to our friends. Okay, we're doing what we call mini presentations, and it looks like we've got about 3 tonight. Okay, and it's kind of like, you know, our main speaker didn't show up, so we're going to go do these instead. So Alan's going to give a 10 or 15 minute talk about
deep reinforcement learning. Right. All right. So I'm Alan Dowding. There's my email. This is a project I'm still in the early phases on, but it's an infinitely sized project, so it's okay. So first, a few of my robots on the left there. That's Pooh Bear Bot. It went deep into the uncanny valley. The next one over there is PR2 Lite. We started working on that. There was 4 high school kids and another mentor who worked on that as soon as PR2 was announced. It's taking on Mike Ferguson and his robot Maxwell in chess at the Maker Faire, and he did great. PR2 did awful, and I'll tell you why in a little bit. I was so impressed by his robot, I cloned it and made Roswell. So that's Roswell on the left there, and that's a gazebo simulation on it, which I'm using for part of this project, which took an absurdly amount of time to actually get working. So I've been doing mobile manipulators with ROS for a long time. And I'm going to talk a little bit really quickly about how it's kind of typically used. So over there is a table, okay? So you have a 3D camera pointed at the table, and it comes up with a cloud of points on it. And from there, you use this thing called point cloud library, and you come up with find the flat horizontal plane, and then you find the objects that are sitting on that plane, and you project them back down to the other plane, and then you can figure out the convex hull, kind of like the circumference of that plane, and then you filter it out by height and by size, and you say, that's a table. Okay. Notice that there's a lot of manual programming here, okay? And it's not always right. This table may not match my tables at home, and it's not an easy thing to do. But that's pretty much what they do in the RoboCut at home. The original Willow Garage stuff, it did that as well, although you'll never find the original PR2 was always pushed to the table at the last end. It just, anyway, that's a digression. Okay. So after that, you find the object on the table. You might use the PCL library to do object segmentation to isolate the object. And then you say you get this object, you look it up in a 3D in a database of known 3D objects, and hopefully when you find it, it'll give you an optimal place to grasp it. Then you go and use Moveit, which is a whole gigantic thing in itself. And you're looking at the table, and you're looking at the object that you want on the table, and you want to filter out your robot arm so that it's not considered an obstacle. And then you look for other obstacles that are on the table that you want to navigate around. And you use inverse kinematics, actually provided by Moveit, to avoid these obstacles. And it plans it all out for you, and it shows you what the plan could be. And then you execute the plan, and it's all blind. It kind of just goes up, and it kind of goes there. And then it does you say, do the final approach, and then you close the gripper. And then finally, you realize you grabbed air. PR2 Lite had overheated servos and started misbehaving that 90-some degree day in Maker Faire, and did horrible. And we can do better than this, okay? Or we want to do better than this. And there's a lot of researchers doing really cool stuff out there. Part of it is you hear about AI and deep learning. And this is some stuff in vision-based deep learning. And they talk about, and most of this has to do with doing very large convolutional neural nets trained on something called ImageNet, which has got like millions of images with labels on it saying what's in the images. And you pre-train these things with the ImageNet to thousands of parameters. And then from this thing, you can reuse this convolutional neural net many, many times, do all sorts of things like image classification, and I only have a few minutes, so I'll skip you. Add a fully connected layer that figures out the probabilities of different classes. You can do add a neural net and do image captioning. You can do image localization, which is like image classification with additional dimensions. You can do image segmentation to produce an array of class probabilities for each pixel. There's a presentation down there I really liked on this stuff. But that doesn't really work for robots. Because what we want in robots is reinforcement learning. Now, some of you may have heard of reinforcement learning for playing Atari games. Now, it's really kind of cool. You kind of have the CNN there, and you train it on pictures, and you add a fully connected layer in the back, and then you can produce one of these 8 possible actions. But it takes 10 million frames specific to that game. Okay, that's 10 times the normal amount that you need to do deep learning on. And then if you change the color of the pong ball from yellow to green, it won't work. Okay? It's not general. And in robots, it's even worse because there's no direct supervision of the robot. Because the robot has to open the door to see if it, it has to reach down and see if it actually succeeded in opening up the door. And these actions have consequences, and you have to reason out these consequences. There's no like pre-made images of this. So ImageNet and those convolutional neural nets are large scale, emphasizes diversity, is evaluated on generalization. What we care in robotics is reinforcement learning, which is typically a small scale, emphasizes the mastery and getting it just right, and it's evaluated on performance. Now, the key thing about deep reinforcement learning, which is it's really cool, is general purpose. You don't actually do all that manual programming that I talked about. It's a big neural net and you train it. And I won't go into the rest there, but the one I'm actually following is something called guided policy search. Now, it does end-to-end training from the 3D, looking at the 3D image, all the way to the actual servo commands. And let's take the shape cube one there. It only required 171 iterations of things to actually produce it. It didn't require the millions of runs. This is why I really love all this work. But I'll give you an example. If you had a cube here, and in the cube is a hole in the cube, and you had to put the peg inside the hole. You use the Moveit commands that I talked about earlier. It missed 100% of the time. You did that with neural nets, kind of combined it with the two. It missed 100% of the time. You did it with this deep reinforcement learning. It figures out that it lines it up on one of the axes, and then it slides it down and it jiggles it in. And it's because it's within the margin of error. The other ones were not within its margin of errors, but that thing, doing end-to-end learning, was able to do something that Moveit could never do. So this is really cool stuff. And I'm not going to, this is just a teaser talk. But the thing that I really liked about this also, they put their code on GitHub. So my goal is to try to reproduce some of this stuff using my robot with the GitHub. This is all by Serge Levin's team. I don't know, there seems to be a few papers coming out. There's at least 6 papers a year from this team. One was last week. It was in the Google blog. So if you go to the Google blogs, it's amazing. It's about robot imitation of people. So when a person bends down like this, it was able to self-train, even though the PR2 or the fetch doesn't have knees or anything like that. It was able to go down and up and things like that. And it also has things that does automatic labeling. If this talk made any sense to you. There's also some stuff on visual deep learning that if you want an introduction to that. I really like this one because it shows also some stuff from NASA which explains how the convolutional neural nets work. So that's my 10 minutes.
Slides on the group, the HBRC mailing list.
I will try to put them in that format so I'll put it in PDF.
Yeah, thanks.
All right. Okay.